Yeah.
Well, it's a great pleasure to welcome you all to this very historic lecture theatre. And really, what a week this has been for physics. 300 years is a major achievement, but we've been treated to some marvelous events last week. I'd like to call out Eric Finch's wonderful lecture, which is very apt to mention because, Johnny, today is the celebration of him as the 22nd Erasmus Smith Professor of Natural and Experimental Philosophy. And Eric took us through the history of the previous 21, some of whom I quote unquote he described as duffs, but not many of them. Only one or two. So I have the pleasure as Dean of the Faculty to do these inaugural introductions. And what I'm struck by at this time of the academic year, Johnny is the last one of 23, 24. So this is about the 8th or 9th inaugural. And what I'm struck by is the diversity. When people come up on this stage from all the different walks and disciplines within STEM, you see the personality of the person, you see what drove them, and you see that there is no one size fits all in science. And that's something very special for Trinity, is that Johnny is homegrown. He's an undergraduate, and as he said, I am an alumnus of this university. So he's a homegrown, he's a scholar, he's a gold medalist, and he stayed here to do his PhD with Werner Blau. And really, I brought this with me today. Yesterday was the position paper that was written on the importance of material science to Ireland. And really, I think material science in Ireland has, to a large extent, built itself around Johnny. And there aren't many people for whom you could say that. So material science is really key to delivering new materials for technologies that some of which we don't even know what they're going to look like quantum technologies and so on. And Johnny's research is in the flatlands, in two-dimensional materials, but there's nothing two-dimensional about Johnny. You always know when he walks into a room, he's great as an ally, he's very challenging as an opponent, his voice is always heard, and there's always a solid reason behind the arguments he makes. And that driven ambition, always with the college at heart, because Johnny is homegrown Trinity. He's loyal to the college and really wants to see physics and the college do well. That loyalty comes across in everything he does. This matters to him. And his research matters to him, and his research group matters to him. And you'll hear him speak out for the situation for PhD students, of whom he would argue many have got him to where he is today, 40 or so PhD students. I always say that H indexes are a challenging thing. You know, you can't look at it and immediately say whether somebody is but a rough rule of thumb is if your H index is higher than your age, you're doing well. And in Johnny's case, it's 124. So multiples of his age, making him one of the most highly cited research scientists worldwide. And the research that he's done is really put graphene on the map. It started with nanomaterials and nanotubes, and then graphenes, and then looked at chalcogenides and looked at surface materials. And what he's doing really at the moment is looking at how you can mass produce large amounts of graphene and look at how the transport across the layers and between the layers in large networks, how you can optimize that. Look at how electron transport occurs across barriers, and that has an influence on things like batteries. And lithium-ion batteries are terribly important for where we're going next in the world as we try and move away from fossil fuels. But I really have said enough. I just wanted to comment on a couple of things. Johnny is a Royal Irish Academy Gold Medal winner in the Physical and Mathematical Sciences in 2023. I had the pleasure of being there and also I took a photograph actually of Johnny and Mike Coey our 2 gold medalists, and it was really lovely to see them both there. So I wanted to just pull that out. And really, I'm just going to hand over to Johnny. He has lots of tricks, as always, up his sleeves and up his gown. And I want to thank you all very much for coming, and please enjoy the event.
So thank you very much, Dean. That was the nicest description of a troublemaker I have ever heard. So thank you very much. So my name is Jonathan Coleman. I'm here. This is my inaugural lecture, and it's tradition that when a professor is appointed to a new chair, that they give an inaugural lecture, and there are different styles of lecture. Here today, my aim is to entertain. The physics has been dialed down to near zero. So some of the physicists may not like that, but hopefully some of the others will appreciate it. Okay, so first of all, a little bit of history. The last week we've been celebrating the 300th anniversary in physics in Trinity. And as Eric will tell you, there was actually physics going on in Trinity before 1724. What happened on the 21st of April, 1724, which was 300 years ago last Sunday, was the first Erasmus Smith professor of natural and experimental, I'm still getting used to it, philosophy, took up his post. And his name was Richard Helsham. He was famous because he wrote the first undergraduate textbook in physics. And that textbook was used in this university up until I think the 1840s. Now, back in those days, we didn't have the facilities we have today. That's the long room library. And that little building up there in the top right, that was where physics was. And that building was shared with medicine, chemistry, and I think a little bit of botany as well. So there wasn't very much space, which is something we still complain about, probably. There have been a number of well, as I said, a number of duds, but a number of famous Erasmus Smith professors. This guy is one of the more famous. George Francis Fitzgerald was number 15. He is famous from a physics perspective for anticipating the Einstein's theory of relativity. He came up with something called, if you're Irish, the Fitzgerald-Lorentz contraction. For everyone else, it's the Lorentz-Fitzgerald contraction. But that became an intrinsic part of Einstein's theory of relativity. So back in his day, physics was in the museum building, which still stands. To non-physicists, he was famous as the guy who flew across College Park. And there's lots of wonderful photos of that. This is before the Wright brothers. Then the 18th Erasmus Smith professor was Ernest Walton, and he is famous. He won the Nobel Prize in 1952, 51. Because he was the first person to split the atom with Cockcroft in Cambridge. So there have been a number of really quite famous Erasmus Smith professors, and he was here in this building. And in fact, there are lots of great stories about him. He was a wonderful lecturer teaching right here in this room. I'm the 22nd Erasmus Smith professor. We have better facilities now than they had. So, okay, so this, do I have a laser? So that is the building you're in from the backside. This is essentially the material science building, and that is the nanoscience building or CRAN that's on Pearse Street. So we've got lots of nice toys, although we would like some more. Now, what do I actually do? I'm a nanoscientist, and for many of you, what does that even mean? Nanoscience is the science of the very small. And this is something that people have been studying in earnest for quite some time now, for at least 30 years, if not more. And the reason is, well, first of all, it's new. Scientists want to study what's new. But what's really sort of exciting about it is that small things can behave differently. For example, a piece of gold like you might have in your wedding ring. If you make it small enough, it's not actually solid, it's liquid. So things change when they get small, and that can introduce new and interesting properties. And if you're asking Science Foundation Ireland for money, you tell them that you're going to find new applications. That's what it's all about. Now, many people think about nano and think, well, nano is in big machines, expensive tools, large microscopes, fancy equipment. Nano is something complicated. So You might be surprised to hear that it doesn't have to be. Nano is much closer than you might imagine. And for example, many of us will know that nano can be found in the leads of pencils. Now, the lead of pencil is not made of lead. It's predominantly made of graphite. And graphite is a material that it's been known for nearly 100 years that graphite is what's called a layered compound. It's made up of single atom thick layers of carbon that are stacked on top of each other. And while people didn't know about the atomic structure of graphite, they knew the effects of its layeriness, because in the 1500s, sheep farmers in Cumbria used sticks of graphite, which came from a graphite deposit where it came to the surface. They would take these sticks and use them to mark their sheep in the way that we use pencils. Later on, graphite became a sort of strategic material for Britain because the Navy used it to line the molds of their cannonballs. And the reason for that was because its layeredness makes it slippy, so it can be used as a solid lubricant. So graphite has been around for a long time, and I think it was 1925, an Irish scientist working in London called J.D. Brunel showed categorically that all of these sort of lubricant type properties were because it had this layered structure of one atom thick layers of carbon stacked on top of each other. Now, graphite is a three-dimensional material. But what if you could remove one of those layers of carbon and have it on its own? Such a one atom thick layer of carbon is called graphene. And even though that comes from a parent material, graphite, that's well known, this graphene is a nanomaterial. Now, for a long time, people sort of postulated that graphene could exist, but no one really looked for it because there had been a theoretical prediction basically that said it would be unstable. Any sheet of graphene removed from graphite would be unstable and couldn't exist. Now, in 2004 in Manchester, that was shown not to be true. They showed that you could remove single atom thick layers of graphene from graphite. And what's more, they showed that those single atom thick layers of carbon had this list of superlative properties. The stretchiest material known to man, the strongest material known to man, highest thermal conductivity, all of these wonderful properties. Now, as a material scientist, you often meet new materials that are really good at something. You very rarely, you never meet a new material that's good at so many things. And that is why graphene became such a well-known material, and the Nobel Prize was awarded to Andrei Gaiman-Kostyantynov in 2010 for its discovery and for the demonstration of all these wonderful properties. So nowadays, graphene is used in a range of applications, so people have to make it. So the question is, how is it made? So I stole this graphic from the web. There are 6 so-called pillar methods for making graphene. So there's micromechanical exfoliation, there's carbon nanotube unzipping, which is total nonsense. There's a few others, and then there's this one, liquid phase exfoliation, which is clearly the coolest method, because in this graphic, we get a fighter jet while all the other guys get sort of a nerdy microscope or another thing. The thing about liquid phase exfoliation is that that was invented in my lab in Trinity 17 years ago. And nowadays, this method and its descendants is used to make 65% of the world graphene. That is a lot of graphene. And because we didn't patent the initial production method, we don't see a penny of that. And sorry, Provost. And there's a company that I'll show you later on called Black Swan Graphene that we do collaborate with, and they make lots of this stuff. Okay, so we can think of graphite a little bit like a deck of cards. It's got all these one atom thick layers of carbon stacked on top of each other, and making graphene can be thought of as simply separating out the cards from the deck. Except in the case of graphene, the pieces are a lot smaller than playing cards. Now, how would we do that in practice? So we've got this stack of graphene sheets, graphite, and we want to turn that into individual graphene sheets. So the way we do that is we put it in water, we add some detergent, and we add some energy. And here is a video of the process. So that's a little bit of graphite in some water. There's some detergent in there. This is just called ultrasonic probe. It's delivering ultrasound in there. And that energy is breaking up those little pieces of graphite into billions of little pieces of graphene. And because each of those pieces of graphene absorbs light, the liquid goes black. If you look in there with an electron microscope, you'll see loads and loads of these little two-dimensional sheets. And these sheets here are single carbon atom thick. And in that black liquid, there's probably one with about 16 or 17 zeros after it of these sheets in this liquid. So this is a method that can be used to produce graphene in very, very large quantities. Now, we knew at this point that we had a technique that was scalable, that could be used to make graphene in large quantities. So we were approached by an English firm called Thomas Swan, a chemical engineering firm, to scale up the process. And actually, I was approached at a dinner in the UK, and I have to be completely honest, I had had a few glasses of wine, and the CEO asked me, can you scale up this process? And I said, of course I can. The next day, it was, oh my God, how am I going to do this? So how did we do the scale up? So we used some high-tech kit. Kenwood kitchen blender. Now everybody laughs. Everyone thinks, kitchen blender, what are you going to do with a kitchen blender? I say, do not.
Which is the slowest cycle we have. This is glass dust. Don't breathe this.
Now, the cardinal rule of giving public talks is do not do a live demo. This is almost certainly going to go horribly wrong, so cut me some slack, all right? Now, I was motivated and inspired to do this by a demo I saw Dennis Weir give when I think I was an undergrad, which had something to do with Guinness. I can't remember exactly what you did, but anyway, I'm going to try and follow you. So this is water. This is just ordinary water, bought at an exorbitant price from the train station about an hour and a half ago. The next stage is some graphite. So this is just powdered graphite. See, I was told a heat spatula. There it goes. This is, I was going to say it's very liquid, but it's Tesco lemon. Oh, sugar, that's way too much. This is going horribly wrong as we speak. Right, so water, surfactant, graphite. So something's happening in there. Now, the problem with this, and when we started doing this, this was a real problem, was the foam. And Stefan and Dennis know all about this, and you can put in defoaming agents and stuff, but you don't want so much foam. But you can see the foam is draining, and you can see the liquid there. You can already see it's quite dark. That, when that foam drains, that will be black. And that's graphene. Now, here's one I prepared earlier. Now, when I say I prepared earlier, Jack, where are you? Jack prepared it, but it's tradition for professors to take credit for everything the students do. So I prepared it earlier. So this is some graphene with whatever this is, Tesco done, made about an hour and a half ago. Okay, so you've seen graphene being made. Now, so that stuff in the liquid, you might say, well, it's just black. You could have put black ink in there. I mean, how do you know there's graphene in there? So this is data where we took graphite from pencils, we used fairy liquid, we used a Kenwood kitchen blender, and this is an electron microscope image of some of the things that are made. And you can see these are almost perfectly flat two-dimensional nanosheets. And if you look in with the electron microscope, can everyone see the hexagonal pattern there? That's graphene. So this, in fact, that is almost perfect graphene. It's some of the best graphene we've ever seen, and that was made in that Kenwood kitchen blender. Incidentally, there's a little story. When we first decided to do this, I sent a postdoc up to Argos to buy a kitchen blender. And I'm from Cavan. He was from Scotland. So he came back from Argos with the absolute cheapest kitchen blender he could find. It was a 100-watt kitchen blender, and it didn't work. But I was confident enough to know this is going to work. Go back and get me the second cheapest one, which was a 150-watt Kenwood kitchen blender, and it worked perfectly. And we later found out that there is a threshold power density required to make the graphene, and the 100 watts wasn't enough. Anyway, so nowadays, we did this work with a company, and it wasn't really about kitchen blenders. That was just a demo. It was done in sort of lab scale industrial mixers. And then when we had learned enough about the process, we went to the company in the UK that made the mixers, and we asked them, can we do some scale-up trials in your lab? And this is a scale-up trial where we made 500 liters of graphene. And just to put that in context, before we did this work, the largest volume of graphene ink that had ever been produced anywhere in the world was about 15 milliliters. This was 500 liters. So this was just a new scale entirely. Nowadays, this is all done commercially. There's a company called Black Swan Graphene that have licensed our process. And this is just one of their units. And they've got a big warehouse with a load of these side by side. And there's graphene continuously being produced in there. Now, scale up is important because there are certain things that you might want to do with your materials where you require a lot of mass. You require more than a tiny amount. You require really significant quantities. So that's really why we wanted to do the scale up, to enable us to make things that we wouldn't have been able to make before. And this is the first thing that we made that required a lot of graphene. This is not a pint of Guinness. That's graphene, and there on top, that is another two-dimensional material that is white, often called white graphene, or more properly boron nitride, and it makes a nice little head. Now, the color of the boron nitride is just a little too white for it to be Guinness. So, you know, there was no danger of a postgraduate student coming in and drinking that and keeling over because it just doesn't look quite right. So boron nitride isn't the only other layered material beyond graphite. In fact, there are about 2,000 of them. And the real strength of this process for making 2D materials that I've been showing you, there are many processes for making the 2D materials, but this one can be applied to all possible layered materials. And this is a photo that was, this is quite old now, this is from maybe 2016, and this shows you where we had got to by then. But we had made quite a lot of 2D materials even then. So there's graphene, this is called black phosphorus, boron nitride, titanium diboride, gallium sulfide, a load of chalcogenides, oxides, hydroxides, layered silicates, talc, bought in Tesco. But anyway, so we can make a whole host of different 2D materials. Now, as I showed you with the blender, the way to do this is you mix the graphite or whatever 2D material you're talking about with water and surfactant, add a bit of energy, and you get this sort of sheet sliding off the graphite, and you get this ink with loads of nanomaterials. A paper came out at some point showing that you could also do this with solvent mixtures. And the paper described a solvent mixture that was 40% ethanol and 60% water. And one of my postdocs at the time said, I know something that's 40% ethanol and 60% water. So one of the professors here in physics at the time, his wife's brother owned Teeling's whiskey. So we said, can we have some whiskey, please? And they said, no problem. We only needed about half a bottle. They gave us a case of whiskey. Now, actually, 11 of those bottles of whiskey mysteriously disappeared. And I still haven't found out where they went, but they certainly weren't used in experiments. In any case, this is graphene exfoliated in Teeling's whiskey. That's tungsten disulfide, another 2D material exfoliated whiskey, and that's boron nitride, and it works a dream. So we don't just use household liquids to make 2D materials. We can use household materials as the 2D materials. And the first we attempted was cat litter. Because as anyone knows, cat litter is made of clay, and many types of clay are two-dimensional. And if you look at the side of that box of cat litter, it'll tell you what's in it. And those red ones are known to be layered materials, which should be convertible into two-dimensional nanosheets. So what we did was we took the cat litter, we ran it through our process, we got an ink, we looked in the ink with the electron microscope, and can you see just about there's very thin objects there? Those are two-dimensional flakes of montmorillonite. So these are 2D materials made from cat litter. But I felt that really wasn't so much of a challenge because we knew there were 2D materials in cat litter. We wanted a bigger challenge. And that presented itself in around 2014 on holidays in Kerry. So we're on the beach, Sneem, and the kids were digging. They dug a big hole. And then one of them said, there's something weird in the bottom of the hole. And I had a look, and there was clay. I don't know what there was. Any geologist here can tell me what there was clay doing a foot under the sand on the beach in Sneem. But anyway, there was clay. So being the nerd that I am, I collected some of the clay, brought it back to the lab. That's an electron microscope image of the clay. And can you see the sort of layered strata? And that shows that there are layered materials in the clay. We then ran the clay through our process, and you see we found lots and lots of 2D materials, and these are mica. Not very exciting, but 2D materials made from clay found in the beach in Kerry. So I think that's pretty cool. Now, I would hate at this point for people to think that physics professors just fart around with kitchen blenders and go into the beach in Kerry. We actually have to do a bit more than that. And I'm really giving you the entertainment version of this story, but everything that we've done is grounded in physics. And for a physicist, what that really means is trying to understand the processes that you're running and the things that you're making. And usually we do that through theoretical models. So I'm not going to bore you with theory or equations, but I just want to show you that this is more than just cookery. So these are some of the examples of the equations that I, and with some help from the students and postdocs, have derived in the course of this work to try and understand the process that I'm telling you about. But that's enough of that. So now, we've made all of these inks, these black liquids or white liquids or funny colored liquids. What are we going to do with them? They have to be useful. That's for what is the question. So the easiest thing to do is to take these inks and print them onto a surface. And in fact, this was a great case of sort of a cabin modus operandi, because there was a skip beside our building and there were a load of printers in the skip. So I sent one of the postdocs to root around the skip, and he found a Canon inkjet printer in the skip that had been thrown out, took the cartridges out, emptied the cartridges, washed them, and put the graphene ink into the cartridge, and he printed this. Now, this is our logo, and actually this looks terrible because this was the first time graphene had ever been printed. We're a lot better at it now. If you look in at what was printed with the electron microscope, you can see it's just a mess of 2D sheets just sitting on the surface. So it's a bit messy, but this was the first time, so that's okay. Now, many people have asked me, why the hell would you want to do that? So there's something called printed electronics, which is all about taking electronic materials, putting them in liquids and printing them on surfaces and fabricating electronic devices from those printed surfaces. And the idea is that you can make electronic devices at an absolute fraction of the cost that they're made out in Leaks by Intel. Now, they won't have the performance of silicon-based devices, but they will be good enough to do a whole host of applications, and they'll be super, super cheap. So this is a big field, and the idea was that the inks of 2D materials that we've made could be useful in printed electronics. So a little bit of a tutorial in electronics. This is not even Electronics 101. This is Electronics 1.0.1. So transistors are probably the most common, and some would argue the most important components in electronics. They are the little bits that make up your computer. So transistors are combined together to make logic gates, which allow computation, and that's the base of computers. So from a material science standpoint, Transistors rely on semiconductors. And to put it very bluntly, semiconductors are materials that just don't conduct electricity very well. They're rubbish. Unless you play a trick. And so you play a trick, you've got a semiconductor, and it's sandwiched between two electrodes to put current in and take current out. But if on top of that, you add an insulator and a third electrode called a gate electrode, what that does is, by applying a voltage to the gate, you can cause a current to flow in your semiconductor. And what this really is you have a switch. By controlling the gate voltage, you can control the current flowing in the transistor. And that sort of property is manipulated in the electronics industry to do all sorts of things. Now, the question is, and this is a sort of a modern transistor where these are now made in Intel, where the semiconductor is not centimeters long, but is nanometers long, millions of a millimeter. So can we make transistors by printing our inks using a printer found in a skin, and the inks being made in the kitchen blender? So the answer is yes, but what inks do you need is the first question. So to make a transistor, you need conducting 2D materials for the electrodes. You need a semiconducting 2D material for the semiconductor, which is the base of the transistor. And you need an insulating 2D material for the insulator. And luckily enough, 2D materials come in all possible flavors. So we've got all of those and we can make inks from them. So now it's a question of printing these inks into the right patterns to make the structure that defines a transistor. Now, so how do we do that? So there's the structure that you'll see in a textbook for what's for the aficionados, that's a MOSFET. This is the graphene source and drain electrodes. Then we printed on top of that molybdenum disulfide, which is a semiconducting 2D material. Then on top of that, we printed boron nitride, which is the insulator. And then on top of that, more graphene, which is the gate electrode. And the idea is you apply a voltage between source and drain, no current flows until you apply a voltage to the gate and then current starts flowing. This is an electron microscope image of the stack. That's the MOS2 on the bottom and the boron nitride on top of it. And this is the current flowing as a function of the gate voltage. Now, it's not the best transistor ever made. In fact, I'd venture as far as to say it's probably the worst transistor ever made, but it is the first transistor ever to be printed from all 2D materials. And now this is a whole field in itself. It's moved on a long way since then. So nowadays, what we're doing is there's something called wearable electronics, which is that you'll have electronic devices and components in your clothing. And they'll do a host of different things, from health monitoring to having your phone in your jacket. You can't drop it when you're on your way home from the pub. Now, the concept that most people have is to deposit the electronics on top of the fabric. And then the challenge is to make the electronics flexible. But one of my postdocs who's here in the room, Tian, had a different concept. He said, why can't we make the fibers of the clothing into the transistors? So the idea was you take a fiber, a cloth fiber, and you coat it with 2D materials, you have electrodes, and you have a transistor. So this is a piece of polyester fiber coated with 2D materials just by dipping into an ink. You can see, look up close, you can see these are the 2D materials sitting on the surface. And this is a transistor response, and it's actually quite good. So around now, the record for performance in a printed transistor, as determined by the mobility, which the physicists will know what that means, is around 10 centimeters squared per volt second. These ones go up to about 15, 20. So these are beyond state-of-the-art printed transistors, and they're printed on the fibers, the very fibers of the clothing. So I think that's pretty cool. You don't need liquid to make these things. So this is a nice little video. Disulfide. So this is a layered material, and you're taking a lot of dilute. And you take some of this layered material, like rubbing it on my hand. And when he rubs it, the layers of tungsten disulfide rub off and stick to the plastic, and you get quite a nice and surprisingly uniform film of tungsten disulfide monoplastic. So this is a similar film with electrodes on it, and the question is, will this film made with a Q-tip work as a transistor? And actually, it's a wonderful transistor. It's really nice. That is a lovely transistor response curve. So that works amazingly well. Now, everything I've showed you up to this point has been about taking 2D materials in inks and using a printer or Q-tip or just dipping to deposit them on a surface, and you just get a pile of 2D materials on the surface. So there is a question as to what is the structure of that pile of 2D materials on the surface. And from a physics standpoint, we really need to know how they're arranged on the surface. So how do we do that? How do we look in and find out how all these things are arranged on the surface? So this is not kitchen physics, but I'm going to show you anyway. And the inspiration came from this chap, who was executed in Texas in 1993 for a rather grisly murder. And the night before he was to be executed, priests went into the cell and convinced him to donate his body to science. And he agreed. Not sure he would have agreed if he had known what they were going to do to him. So they froze the cadaver and they cut it up into 1,871 very thin slices. And they took high resolution photos of the slices and they put them together to form three-dimensional images of this man's body. And these are used for teaching and other purposes. So the idea is, could we do this with our film of 2D materials? So this is a method. So that is an electron microscope image of the top surface of a film of 2D materials. And that's an electron microscope image of the side sort of into a cross-section of a film of 2D material. But what we'd really like to do is look inside and have a 3D image. And this was really hard, but this was developed by Cian and Luke, who are here somewhere. This took a long time. I think this started before COVID. Okay, yeah, it's all right. You got through it. So the idea here is you take an electron microscope of a cross section of such a film, and you then slice off a very thin layer. Take another electron microscope image, slice off a very thin layer, another electron microscope image, and you do that about 1,000 times. And then in the computer, you can combine that 1,000 images into a 3D image. And this here is a 3D image of a printed film of two-dimensional silver. And this image contains over 1 billion data points, but contains all of the information about the structure of that film. And that then allows you to model the film and learn about its physical properties and understand why it does the things it does. So this was a really important development that was published just in the last few months. So now I just want to finish by moving away from these printed networks into something different. I want to talk about polymer composites. So there's a lot of work in the field of 2D materials, taking graphene, which is the strongest material known to man, and putting it into plastics with the idea of making them stronger and tougher and stiffer and all of that stuff. And a few years ago, a tennis racket came on the market, which was marketed as having graphene in there, doing wonderful things. The reality is there was probably so little graphene in there that it did absolutely nothing other than allow them to add €50 to the cost of the tennis racket. But nevertheless, you get the idea. So Cavalman Joe is shaking his head in horror. So a lot of people were doing this work. This was a very big sort of area of research. We decided with Connor, who was a postdoc at the time, who's here somewhere, to do the exact opposite. We decided, rather than taking graphene and putting it in a strong, stiff polymer, let's put it into the softest, weakest, crappiest polymer that we could possibly find. And that was the children's toy Silly Putty. Hands up here who played with Silly Putty when they were little. Don't be shy, more of you than that. Come on now, loads of you. So we all know what silly putty is. So Connor made his own silly putty. It's really easy to make. The recipe is really simple. This is silly putty. It's that color just because it doesn't have the dye that they put in it. And this is silly putty with about 10% graphene. And when you do that, you get, that's the commercial stuff, and that's our graphene silly putty. It's super stretchy. And that's my younger son, who was briefly famous when this image went viral in China. Now, what I'm usually asked at this point is like, why would you want to do that? So the reason is, if you take this super soft composite and you stretch it, something really unusual happens. You stretch it a very, very small amount, and its electrical resistance, it conducts electricity because there's graphene in there, and graphene conducts electricity. You stretch it a very small amount, and its electrical resistance changes by a huge amount. 2% stretch, 500 or 600% change in electrical resistance. And that's useful because what you have now is a sensor. You have a sensor that can detect mechanical deformations and give an electrical readout. And what's more, this is the most sensitive electromechanical composite sensor ever made. So it must be useful for something. So this is Connor, and he's got a piece of the graphene silly putty there. There are wires coming down into a measurement device. He's pushing it up against his carotid artery, and on the screen is the electrical resistance of the silly putty. And you can see those peaks that are sort of forming there. Those are being formed because the pulsing of his artery there is compressing the silly putty, causing its resistance to change, and that's being detected there on the screen. And in fact, it's pretty amazing because this is part of a trace. You see these little dips? Those are called the dicrotic notch, and they represent the pressure change when the aortic valve closes. And we can detect that really nicely. And in fact, what's more, by measuring the size of the resistance change, we can measure blood pressure. So these are really, really nice potential medical devices. Now, we can do other stuff. An engineering student came to me and said, I'd like to do a project with you, and I want to use this silly putty stuff to make sensors for use in sort of the mountain bike. Like my brother, this guy was a mad mountain biker. And I said, you'll never be able to do that in the 6 months you have. You know, pick something sort of easier. And he said, no, I know what I want to do. So I said, right, knock yourself out. And he bloody well did it. So this is something, a little video that we made. So do you see there, that little black strip? That is a piece of the silly putty. And what's happening is that when you pedal the bike, the sort of forces you exert on the pedals are transmitted into the frame of the bike and cause tiny little warpings of the frame. And this sensor is sensitive enough to pick up the electrical resistance change in the silly putty due to the warping of the frame. And you can see here as he speeds up, the oscillations get quicker. So from these oscillations, we can measure the speed of the cycles, but not just that. From the height of the oscillation, we can even measure the power output that the cyclists go. My brother is a mad cyclist. I presume you would pay a lot of money for something like that. Well, actually, he's from Cavan, so he probably wouldn't. So finally, just to finish up, they say never work with children or animals. But that didn't deter Connor. Where are you, Connor? There you are. So we really wanted to demonstrate the sensitivity of this graphene silly putty sensor. So how could we find a test that was going to be really sort of visually impressive, but really sensitive? So Connor said, no problem, I'll figure out something. So we went to the library, which all the books and journals are online, so not many people go to the library. So it's a dusty sort of quiet place where you find lots of spiders. And he found a spider. And the idea was you get the spider to walk across the sensor and we would measure the footprints. Now, the original idea, if I remember correctly, was that he would find two spiders, a big one and a little one, and you'd be able to see the big footsteps being big sensor readings and the little footsteps. But what actually happened was he caught a big spider and a little spider, put them in a box together, went off and set up the experiment, and then came back and there was only the big spider left. The big spider had eaten the little spider. So we only have data for the big spider. So this is the spider walking on the sensor. It really didn't want to be there. It didn't like the feeling of the stuff under its footsteps. But with a lot of prodding and poking, it was convinced to walk across the sensor. And this is the electrical resistance of the silly putty. And you can see those spikes are individual spider footsteps. Now, in science, we are always told that your experiments have to be repeatable. This experiment was not repeated. It was hard enough to do it once, so we were happy enough with that. But there is a serious side to this. This sensor was made from a children's toy, silly putty, mixed with graphene that was made in a kitchen blender. And yet, we were able to produce sensors that were the most sensitive pressure sensors ever made using soft materials. And that's down to the power of nano. And I think that is remarkable. And if you remember one thing coming from this lecture, that's what I'd like it to be. Okay, so that's it. So I'm the guy standing here up front looking daft and taking all the credit, but in reality, all of this work was done by a bunch of exceptional students and postdocs down the years. This is our most recent group hike. This is a refreshment break in Johnny Fox's. I said 1 pint only before we move on. I was completely ignored. You can see the happy faces. These are the guys that did the work. And of course, I have to thank the people that funded the work. And of course, thank you for your attention.